The talk through for the C programming lab. Over on my left hand side here I have an instance of my Kali machine. Over on the right hand side I have some of the notes. This isn't a talk through of how to program in C, it's just some of the most important things that I think you should be aware of. So in the Kali machine you'll need to use a text editor in order to edit a text file. That text file will contain your C code. The text editor that I use is VI or Vi. It may be that you wish to use something which perhaps is a little bit easier. Some students like Nano for quite a heavy application, but perhaps easier to use. Maybe that you want to use something like Kate or Gedit, but the demonstrations I use here are with VI. So the very first example that I give is using CC in order to compile some code. The input file is called test.c. That will generate a binary, an executable file. It's called a.out. So instead of having lots of binary files called a.out, it is possible to specify the name of the output file. And here's an example where the output file is called test. In order to run that, as long as we're in the same directory as test, we can use // and then the name of the binary file test. There's some more flags that I've got here. So -G is useful when we're using GDB, -W is going to suppress any warnings, and we can compile for a 32-bit or a 64-bit processor. Most of the stuff that I'm going to do will be compiled for a 32-bit processor. The reason for that is so we're only dealing with 32-bit addresses, so 4-byte addresses, and we're only dealing with 32-bit registers in the processor. It just saves the memory addresses are half the size as they are on a 64-bit processor, so that's why I compile for a 32-bit. And then down here you have an example of that. So I'm compiling, my input file is called test.c, my output file is going to be called test. I'm using the -G flag, the -W flag, and I'm compiling for a 32-bit architecture. So a little bit later on I give the outline of a basic C program, and as you can see here I need a main function. I'm returning a variable of type integer, so it's going to pass control back to whatever has called it. I also have some inputs into my main function, so I have inputs that are coming from the command line that I'm executing this function from, or whatever else I'm executing this function from. In this case it will be the command line. I have a count of the number of arguments that are on the command line when this binary file is executed, and I also have an array of strings. So I basically have a two-dimensional character array which contains the values of the arguments that are passed on to the command line in executing this binary file. That means I can pass some flags into the binary file to do various bits and pieces. I'll show you some examples of using these structures a little bit later on. But we always start with hello world, and in order to print out hello world I'm using a printf function that exists in the standard input-output library. So I have my main construct, I have some includes, and then I'm passing some text into my printf function, and the text is hello world. So that's all pretty basic, and we move on to declaring variable types, and I give an example of declaring a variable type integer, multiple variables of type integer, so x, y, and z, and then I'm able to assign values to those variables that I've just declared. I can do exactly the same thing with floating point variables. I then move on to characters, and I give you an example of declaring some characters and then assigning values to those character variables. So here I'm assigning the variable x, the character a. Here I'm assigning the variable y, the character new line, and here I'm assigning z, the character 5. And it's just important to note, if we go to our ASCII table here, that we have characters that might look like numbers, but they are actually represented as characters. So the decimal value for 5 is 53. Hex, which is a sort of thing that would find if we looked at this in memory, will be 35. So it's very different to an integer value 5. It's actually an ASCII value of 5. I then move into talking about some arrays. I give an example of an integer array that you should really be familiar with. So I have a 4-element integer array, and I'm assigning values to each of those elements. In C we count from 0 to 1 less than the size of the array. Sorry. That's sometimes confusing for some students. We declare an integer array with 4 elements, but of course we never actually put anything in element which has a 4 in it because we're counting up from 0. So our first element in the array is actually 0, second element is 1. Now, I'm then able to print out various parts of the array using this printf command here. I then move on to arrays of characters, otherwise known as strings, and these are relatively important because they do need to be terminated by a null character. Now, as a little bit of this, my null character actually occupies one of the parts of the array, and if we get the management of arrays of characters incorrect, it may be that we end up with something that's referred to as an off by 1 error. And so if, as opposed to attempting to assign 3 characters here, if the programmer attempted to assign 4, if we're dealing with it as a string, it means that we have an expectation, or it would automatically be terminated, depending on your compiler, by a null at the end. I then move on to some of the most interesting things that we are looking at, and that is anything where we're able to control memory. So we have pointers. Now I've declared a pointer to a character here, which means my x variable is going to contain a memory address. That memory address points to another memory location, which has had an area reserved, which is the size of a character, which in this case would be 1 byte in size. Now I give a little bit of an explanation here. I then go through the process of doing some weird and wonderful things that you probably have never seen in any other programming language. So I'm declaring what looks to be 2 variables of data type int, actually because I have this star, this asterisk next to it. Do I refer to it as anything up here? Yeah, the star. I'm declaring this as a pointer to an integer, and I'm then declaring y as being a standard integer variable. I'm putting a value into y, and I'm making this pointer equal to the memory address of y. That means that when I deal with x, I'm actually able to look at the contents of y, because x points to the memory location of y. Now this leads us to do some interesting things. Because x is pointing to the memory location of y, when I print out the value of x, I'm actually getting also the value of y. And if I change the value of y, we'll see in a little while when I print that out, it means that I'm actually changing the value of x as well, because x is pointing to the memory location of y. So C is great fun. It's fantastic for identifying and exploiting vulnerabilities because of weird and wonderful things that you're able to do with memory, and also because of some of the functionality of C having undefined things that happen in the case of not handling exceptions correctly. So I ask you to look at this, go through, talk a little bit about allocation of memory at runtime, and I no doubt come to a point here where I say, right, this is going to be a complicated thing. We are now going to declare a variable which is input. It's a pointer to an integer, and what I'm doing is I'm now allocating space on memory, which is the size of an argument that is passed in to this function when it's executed. So in this case, I've now introduced something that may be an error, because I'm not handling when there is no other variable passed in. I'm not handling sizes of 0, and I then attempt to use something that's been allocated on memory, and then attempt to free something that's allocated on memory, which may cause me problems. I do mention this just a little bit below that. I then run through the process talking about conditional statements, which should be very, very similar to the sort of thing you've seen before in Java. So both conditional statements with if, looping constructs with for, looping constructs with while, and then in the lecture I ran through something simple with a function. So I actually have test.c, and in my test.c I have stuff which is relatively complicated that I just want to draw your attention to. So I have my standard construct. I'm including my standard IO library. I'm passing some variables into my main function that have come from the command line when this is executed. I have this that I was talking about earlier. I have a pointer to a variable called x. I have a variable called y. I'm assigning a value to that variable called y. I'm not using this, but I have a character called L. I'm giving that the variable character A. I have a floating point number. I have an array of integers, I have a pointer to a set of characters that is actually assigned to a pointer which is the second element that is input on the command line. My second element, of course, being indexed by 1 because we start at 0. I then specify a string, which is a character array, 4 characters. I put some characters in there, and I explicitly state that the last character in that character array will be a null character. I then print out my character array. I do this nice thing here. I make the memory location of x equal to the memory location of y. I put in some values into my integer array. I have my printf hello world. I'm actually printing out the dereferenced memory location at x and y, changing y so I can see the change in x and y. I then print out some input because x is a pointer to a character array, and I make that equal to one element in my two-dimensional array, which is argv, so I'm able to see some input from the command line. And I'm actually able to deal with this. This is the most complicated thing that I just want to draw attention to. So I have a pointer to an array. I'm then able to use that pointer as if it were an array. So I can look up individual elements in that array. So this syntax may be something that you haven't seen before, that you're not familiar with. I can just run this once, just to have a quick look at it. So I have been through the process of compiling it. Let me just compile again. With a few flags as well, so I can then run my program and I can type in, I don't know, a few characters, and I have my name being output, so this is a character array that I initialized. Of course the last character is a null character. I print out hello world. I have my x and my y, where x is pointing to the memory location of y. I change y, that changes the value that I've got in x. I'm able to print out the second element in the command line. Remember that we're looking at the second element. This is the first one indexed at 0. This is the second one indexed at 1. And I'm able to look at that second input on the command line and treat that as an array, so I can take out the first element in that array, which in this case is t. Should I decide to type in something else, we can see that I'm able to index some other characters here. I then ask you to write a C program that will take an input from a user and reply whether or not that input is a prime number. That requires you to look up a C function in order to take some input. Here's one I prepared earlier. So I happen to be referencing standard IO and standard lib. I am unsure what I'm picking up from standard lib. It may or may not be this modulus. I'm not passing anything into my main function, so I'm no longer passing parameters in or arguments in from the command line. I have some declaration of some variables, and then the function that I haven't given you to play with before is called scanf. So I'm going to scan in an input value from the user, and I'm going to put that in my variable input. And I have this ampersand sign here, which sort of says what I'd like to do is I'd like to put it into the memory location that is indicated by input. I then have a very simple algorithm. I'm looping through some numbers. I'm doing a modulo on my inputted number and on the looping values. And if I find that my inputted number is divisible by my looping value x, then I've identified the fact that whatever is input is not a prime number. I need to draw your attention to something that I'm using here, which is a return value. You may or may not have used these before, but this means return from this function to the calling function. And in this case, because I'm returning from main, I'm returning to whatever called it, which was, in this case, terminal. And if I actually get through all of this for loop, and I haven't broken out of the program, it means that the input value happens to be a prime number. So again, I should be able to compile this and run it so you can see it. Prime.c minus g minus m32, and then when I run it, what am I asked for? Please enter a number. Let's put in the number 5. 5 is a prime number. So 5 is a prime number. That's very good, isn't it? Let's put in a number that isn't a prime number. That's 6. How long does it take if I have slightly larger prime numbers? So a couple of nice prime pairs here with 821 and 823, and then let's just put in a very large number. That's going to take quite a long time because I'm going through, my algorithm isn't particularly fast, but we happen to identify the fact that, ooh, what's happened here? My input number doesn't happen to be the same as the number that's indicated here. Now, we will find out what has happened as we go through this unit. A little bit about what I've just identified here is actually in the next laboratory, which is on GDB. Thanks for listening.